Okay, welcome to the Civboot podcast. I honestly don't remember what episode this is. It's been like a year or something since I last did anything. I'm excited to start again. One of the reasons I'm starting is because I finally have something worth talking about, I feel like. First, I'd just like to talk about my setup real quick because, man, I had like the worst setups. So, what I'm doing right now is I'm just using this simple screen recorder, which is just recording this screen. Nothing fancy there. And I just have VLC open. Uh, right clicked to always on top here. And you know what? It's really slow right now. One second. Oh, I was just running some other video processing there. And it didn't like that. Things were getting really laggy. All right, so this is a fungi introduction. I'm excited to announce that I have finally built my third version of fungi. I'm starting to write fungi code. I actually have live coding sessions up if you're interested in that kind of thing. Personally, I think it would put me to sleep, but I thought maybe someone would like it, and it lets me have a chance to sit and talk. This is an accompanying blog post for that. It's on the civboot.org website under blog, which is under the Civboot GitHub repo. I've started to write fungi code, so you can go over to fungi and check it out. Warning, it's in the alpha stage. It basically is unusable at the moment. But I think a lot of the concepts are really laid out very well, and a lot of the architectural decisions, it's just coming together very well. So, what is fungi? And this is the introduction podcast for that. Fungi is my personal attempt at creating a minimalist but understandable programming language for Civboot that's usable even on minimal hardware like microcontrollers. And the primary thing that distinguishes it from a lot of programming languages is that there's no virtual memory management required, meaning you don't need contiguous memory blocks in fungi in order to not have fragmentation. And basically, as far as I know, there are no programming languages that fit that bill at all. Unless you count ones that literally just don't care about memory management at all, which is like Forth. They just pretty much say, it's up to you. I don't know. So I want to give a preview of what it is and why you might want to use it. If you're listening, this is going to be mostly focused on podcasters. So I'm going to try and steer clear of like explicit coding examples. You can go ahead and read the blog, look at the code. I'm going to focus mostly on the oral parts of this. So what is fungi? It's imperative, strongly typed, compiled, low-level language. And we're going to get into each of those, what those mean. And this is just going to be the first part of the podcast. I'm going to be doing each of these in more in-depth episodes. So what is it? It has a syntax and requirements similar to C, meaning it defines structures, pointers, how to access those, how to pass them to functions, how to return them from functions, etc. All that fun stuff. It has an implementation architecture very similar to Forth. If you've ever implemented a Forth, you know that it can be done in about 1,000 lines of assembly. Fungi is not quite that tiny, but it draws from a lot of Forth's better features, better design decisions, to make the compiler extremely lean. And the parser extremely lean. And I'll get more into that in a future episode probably. And it has a type system. Yes, it has a type system. It is not a Forth, which draws from the simplest and most useful ideas of Rust, primarily, but also other languages. Like, I quite like Golang's ideas of interfaces, although I don't necessarily like how they implement them. Also, it is a macro-first language. What does that mean? It gives maximum power to the programmer to extend the syntax or access the compiler internals, like the type system. This is an extremely rare feature in programming languages. I think the only ones I know of that really do it are Forth and Lisp. So it's one of those languages. So there's a lot to unpack here. So first of all, the tiny implementation. The Fungi compiler today is only about 3,000 lines of code. It's written in C. And I don't believe it's going to get much larger. That's the base compiler before Fungi starts compiling itself and defining its own standard library. actually defining itself, bootstrapping itself. Yeah, and this is pretty much in line with many forths. I mean, it's not as small as Forth, but it packs several more features that Forth does not. So I think it earns those extra lines of code. Its syntax is kind of like C, but it does not follow C in any specific, way. So it has some mundane differences, like it doesn't use braces or parentheses, and it doesn't have things like precedence, ordering precedence for operators. But Fngi code reads remarkably like C. This despite the fact that Fngi is compiled in a single pass. And we will get to that in a future episode, but basically its compiler and tokenizer is as simple as you can possibly make anything, as far as I can imagine. Yeah, let's continue. Types. It has them. It also has pointers and double pointers and triple pointers. Typically the types are checked at compile time, although you as a programmer can disable it. And you can, as a programmer, can also directly alter the type system using syntax functions, aka those powerful macros we were talking about. They're called syn functions, S-Y-N. Types will include structs, or they do include structs, and they will include enums. They're exactly like C structs. You can package a set of named things, such as integers or other structs into your own type. And enums will be like Rust enums. They're a value, and they contain exactly one of some set of types. So you could have an enum that could be an integer or string or, a dog. It could be any of those, but it's only one of them at a time. And you have to unpack that. And the compiler will help you unpack that. All right, so it also has data inheritance. Now we're getting into some real interesting stuff. This is something C does not have. This is something Rust does not have. This is something like C++ has. Basically, data inheritance is kind of like single inheritance, but it's slightly lighter weight. The main difference of it is that data inheritance means that if you inherit from something that you contain all of their data fields, and any of their methods that you don't override are valid. This is most useful for things that just extend data types, like if you have a string, which has some data and a length. So it's, a data pointer and the length of that pointer, the length of the data at the pointer. And you want to make a buffer as well, which also has a data and a length, and it has a cap. Well, anything that you could do a slice is valid there. I discourage you from using this for any kind of fancy object-oriented programming. This is just for cases where you have data and then you have more data, and all of the methods that applied to the data you had originally still apply, but then the more data lets you do some other stuff, like, I don't know, grow your slice. It also has something called roles, which are kind of like interfaces. Now, interfaces sounds like, oh my gosh, this is getting too complicated. How could you call this like a fourth? Very easily. An interface is just a struct of method pointers. Other languages use various lookup table things. They have to deal with all sorts of complicated stuff because they can they can have a type that implements multiple interfaces and then can be passed to a function that takes a type that implements multiple interfaces, and maybe they do code gen. Fngi doesn't do any of that stuff. If you want to do code gen, the macro system is wide open for you. Feel free to make a macro that does code gen. There will be, string macros, which will look a lot like templates. You can do type checking in your macros. You can do whatever the heck you want. So if you want to do code gen, that's wide open. And that's essentially one of the things that a type system does. let's talk about a little bit about type systems, actually. There's two things, in my opinion, that type systems really do well. They make it so that code that's mostly similar, but with just slightly different types, you can automatically generate new code. That's all it is. It's basically a very clever and safe macro system. Or you have dynamic types. Those save code size. So one of them actually generates a whole bunch of code. You think you only wrote a function, but if you implement 30 types, you actually wrote 30 functions. Congratulations, that's a lot of code. In one of them, you implement a single function and it takes a dynamic type, and you really did only implement one function. But there's some added cost on lookups at runtime for that. And this is what Fngi roles do. So there's a little added cost on lookups, but it's only a single pointer dereference. Not too bad. It's a pointer offset and dereference. So, for instance, the method drop is of a role resource would be at pointer offset 0, and if there's another method, that would be at pointer offset 4 on a 32-bit system, 4 bytes. And then you could implement a Unix file, which has some data fields. It's a structure. And then you could implement the drop method on the Unix file, which maybe calls close, and then maybe freeze itself or something like that. And then you say, hey, resource is implemented for Unix file, and the drop is just the Unix file.drop. And actually, the compiler can infer that pretty easily, so it's not required. But and you are just defining a struct which has the drop method implemented, drop method set. That's it. It's a struct with methods, and then a role contains that method struct, and it contains a data value. And so it will just pass that data value to those methods as their first argument. And that's the entire, that is not complicated. This is not highly challenging. This can be done. All right, let's move on. Syn functions. This is by far where Fngi diverges from most programming languages. And like I said, Lisp and Forth are the only languages I know that really do this well. Maybe some languages like Tickle or something. It is definitely Fngi's most extreme and dangerous feature. You can call any Fngi function and read and modify defined global variables at compile time. Wow. I may add the ability for you to mark certain ones as you won't be able to do that. But what can these functions do? They can control the parser. They can call other functions. They can parse tokens, or they can parse custom syntax. They can literally control the source file. They can read it byte by byte if they wish. They can write bytecode directly to the current code location, which is a virtual machine language called Spore. So they can write Spore to the current code location. They could probably also compile their own native code or something like that. I haven't defined how that would work, but I think that's definitely possible. They can control the type database, including they can push and pop types. So does this mean they can control how types are compiled, literally? And then actually, this is how the if statement and the while statement will be implemented. They are implemented. The if statement and the while statement, which is actually called the block statement, I'll be implement while on top of block, are implemented as syn functions. They're not built into the compiler per se. They're just implemented as a normal function. And so this goes way beyond the text-based languages like C. Although Rust does have something kind of similar, which you could read about. I forget what they're called. Procedural macros, that's what they're called. So this is how I'll implement things like while, switch case, and maybe even have text macros, which I kind of like text macros. I know they're frowned on. All right, and then the final point, Fngi is low level. It brings low level programming to a whole new level. Like C, Fngi requires manual memory management. This is not something common in a lot of new languages. Fngi does it differently. you pass your own allocators. So it supports custom allocators. This is actually, I think Zig does this. I was very impressed with their design choices. But unlike C and unlike Zig, Fngi's standard library requires only a maximum contiguous memory of 4 kilobyte blocks. So if you think of an array or a string or, I don't know, a list of stuff, there's only guaranteed to be 4 kilobytes of contiguous memory for Fngi's standard library. You could implement your own library, which assumes larger memory blocks. But for the standard library, all of the algorithms, everything will just expect to be working at 4 kilobyte blocks. And what does that mean? That means this can work on microcontrollers in a dynamic type environment, like, I don't know, an operating system. You can run programs, you can edit text, you can do all sorts of code stuff, and it won't cause fragmentation because microcontrollers or similar embedded or simple systems like that Civboot targets probably won't have memory, virtual memory tables. And so there would be memory fragmentation if you could just allocate any blocks of memory. And this sounds complicated, and it, to some degree it is. And it kind of, you can't use certain data structures that maybe you would enjoy. Like, you can use arrays, but you can't use very large ones. Things like that. But really, this simplifies the whole hardware stack. And it also enables things like passing of data more easily in the kernel, I think. I think this will be a good decision going forward. And of course, it can always be grown later. Starting with constraints is better than trying to add them in later. Yeah, so that's Fngi. That's just a quick introduction. Again, there's a blog post you can read if you're interested, and I'm going to continue making podcasts about it here and teaching it as I go. So thank you so much.